The opposite side of the coin from ionization energy is electron affinity. And electron affinity is, let's see if I can write it nicely here. Probably not. So electron affinity is the energy change when an electron is added to a gaseous phase atom. Okay, and so this is the other side. In ionization energy, it's the amount of energy to yank off or pluck off an electron. Electron affinity is the amount of energy it takes to add an electron to it in the gas phase. Again, it's the gas phase, so we don't have to worry about the energistics of changing phase or going from a solid to a liquid or any of that stuff because it's all taken care of. Okay, now this is the measure of an attraction of an electron to an atom. And so electron affinity shows us the amount of energy that is released when that happens. And so because it's a released, if we go back to our thermodynamic brain, that means that it's going to be a negative value. Okay, so that becomes our definition of the system. So the system is, in this case, the system is our atom, and it's stealing it, or it's adding an electron in, and so it releases energy because it becomes a lower energy system. And so that energy is released around it. Okay, so that's what we're looking at with electron affinity. Now there are trends within electron affinity that we're going to talk about very quickly. And so in the trends for an electron affinity, when we look from left to right in a period, generally speaking, the electron affinity becomes more negative. That is, more energy is released, and it's a stronger electron affinity as we travel down the right on a period. So starting over here, working that way on Your Friend of Mine, the Ultimate Party Planning Guide, the periodic table, we see a more negative value, generally speaking. Now, if we look at our graphic here, we see lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. And like fluorine is the most electron affinity, has the highest electron affinity in its row. Generally speaking, it goes from a smaller negative value to a larger negative value, with the exception of nitrogen. And again, like I said, there are usually irregularities, and that's okay. These trends don't include the noble gases. Well, why? Well, if we're talking about having noble gases having an ability to steal an electron or take an electron in, well, number one, electrons have a full valence shell already. They don't want any more electrons. They would have to put that electron in a higher, further orbital away, and they just don't have, they're just not going to do that. They're not interested in grabbing another electron because they don't have the energistics to do it. Okay, and so that's that. That's how we explain the noble gases. And again, if we talk about group 15 elements have unusual electron affinities, and if we talk about group 15 nitrogen, as you know, if we do a Lewis dot structure for nitrogen, remember that's where we are first seeing two electrons paired together in one of the orbitals, and so nitrogen is a little bit weird, and so it doesn't necessarily like to take in extra electrons unless it really, really, really has to. And so that's that one as well. Electron affinities do not change much going down a group. They just don't change a whole lot. And the reason for that is because as we go down a group, that extra electron is being added to a valence shell that is increasingly further and further and further away from the nucleus. And so the nucleus force of attraction is decreasing, and the higher the valence layer, the further those electrons can get away from one another, the more space there is on the outside, the periphery of that atom, and so there's less repulsive forces there. And so, they generally don't change a whole lot. So if we're looking at hydrogen, lithium, sodium, potassium, and rubidium, -60, -53, -48, -7. Okay. If we look at oxygen, sulfur, selenium, and tellurium, they didn't change a whole lot. So that's kind of where that's at. So that's electron affinity.